Welcome back to another lesson with me, Mr. Wong. Today we're going to be looking at Module 3, Reactive Chemistry, Inquired Question 1, Chemical Reactions. Before we start, we need to go through what different types of chemical reactions are as a part of our revision. So we have decomposition, combustion, precipitation, and metal corrosion. So let's try and break these parts down and give a general description of what these reactions are. So, decomposition. Decomposition is when a chemical compound separates from each other to form a small compound or element. The best way to illustrate that is by doing a little symbol equation. So we have a compound, let's say AB. In a decomposition reaction, AB is going to split into small components, A and then B. Combustion. So a combustion reaction is essentially when some kind of fuel source reacts with oxygen gas. It's really exothermic and it's some kind of burning sensation. So if I try to model that, let's say we have a metal mixed with oxygen gas, we get some kind of metal oxide. Okay? That's not the only thing that combustion can do, but we can leave it at that for now. Precipitation is when you have two metal salts and they kind of mix together, exchanging cations and anions. And more importantly, though, is one of these solutions will kind of mix together and form a precipitate. So a solid that also has some kind of color. So it could be AB plus CD, and then C goes with B and A goes with D. And it might be that AB is the one that forms the precipitate, and that would be the colored solid. The last one we have is metal corrosion, and it's almost similar to combustion. You do need a metal plus oxygen exposed into a humid environment, and that would also create some kind of metal oxide. What we're looking at today is the syllabus dot points. We're going to try and look at firstly this little thing up here. So just trying to model out how conservation of atoms in a chemical reaction, rearranging atoms to form new substances. So we're going to try and look at that. We're going to also try and look at a variety of reactions to identify indicators of chemical change. All right, so what we're going to look at today is just identifying indicators of chemical change, and to work that out, we're going to firstly separate the difference between physical and chemical change. This is your textbook reference if you need to read further for this lesson. All right, so let's have a look at what a chemical change is and physical change. Looking at the simulation or animation we have on the right-hand side here, we can see that there is gas production, there is light being produced. So what kind of things do we see in a chemical change? Well, firstly, we see production of light. So production of light. We see that there is gas production as well. Obviously, we can also see some steam coming out, so we can see that there is heat. Let's look at our second one. So if we can see here, we have the formation, well, we can see fuzzing bubbles. So again, gas production, and then we kind of see the gas powder form together, and then we get this nice little solid coming out. So a form of solid, or what we call a precipitate. If we look at another interesting one, this one is actually a physical change with water. It looks quite interesting because you can see it partially boil and then it freezes and it's a liquid. Now, this is one of the interesting things. This is a physical change, but the reason why you can see the water being simultaneously a solid, a liquid, and a gas is because it's reached what we call a triple point. So under certain temperatures and pressures, a compound like water can actually be simultaneously a liquid, a solid, and a gas at the same time. So this is what we've had so far. We know that if it's a chemical reaction, there should be light produced, there should be gas produced, and if there's a gas, sometimes they're odorless, sometimes they have some smell, so you can probably smell it as well. And most of the time they don't smell that great. Okay, so we have physical change, which is a change in appearance, but chemical composition, so the composition has not changed. If it's a chemical change, not only do we see a change in their appearance, but their chemical compositions will also change. If we look carefully, some examples here, vaporizing water, so precipitation and all that, sublimation of dry ice, those are all physical changes. Chemical changes, we have vinegar and baking soda. And we also have burning wood in fire for chemical. So let's look at some of the applications of the physical changes first. If you look at this, evaporation and crystallization. So evaporation, all you're doing is you're trying to get rid of the excess H2O over a period of time. The surface H2O simply escapes the surface of the solution. As more water disappears into the atmosphere, you're left with a saturated solution, and when something is saturated, little crystals will form. And where do they use this? Salt harvesting. So what they use in salt harvesting, they will get a lot of salty water and they'll put it on the plane, and they'll allow the water to naturally evaporate from the surface of the water, and over periods of time what you're left with is just plain solid salt or crystal salt. The next we have is sublimation of dry ice. So sublimation is where a solid turns back into a gas. So a solid turns back into a gas. And you'll see this on some of the concerts you might be going to, where they unleash the dry ice gas out. Next one we have is, let's look at some chemical changes in everyday life. So in most parts, you will come across a lot of different chemical changes. You have the Maillard reaction. So what actually happens is foods that are not sugar or not made of mostly sugar, during a reaction, they turn brown. These result in a savory complex flavor. So when we're cooking, that's obviously a chemical change. Caramelization, that is also a chemical change here. We're changing the chemical structure of the atom. So let's look at some signs of chemical change here. We already talked about a couple earlier on. So we can see that firstly, light production. So if it's a chemical change, we produce light. We also see a permanent color change. So if it's a partial color change, that's not really considered, but if it's permanent, so the color stays, doesn't deteriorate, that is a chemical change. If we have gas production, we can smell it. Those are all different types of ways we know if a chemical reaction has occurred. So if we summarize this, there are 5 basic points that we can look into. So common signs of a chemical reaction or chemical change. Firstly, you have a temperature or permanent color change. So if the temperature has gone up or it's decreased, that may be an indication that it's a chemical change. Formation of light, formation of a solid precipitate in a solution, production of an odor, so production of gas. And let's use a simple example. We have magnesium metal here. So magnesium, when it reacts with oxygen, you would have all seen this in term 1. One of the indicators we see in this reaction is a production of a really bright light. You could probably also see some gas forming at the very top, and then we have this magnesium oxide here. There's a little video that shows you really nicely the chemical reaction or combustion reaction of magnesium, but I'll leave that for you to watch in your own time. Links will be in the descriptions. So what's actually happening in a chemical change at a molecular level? Let's compare the physical change of water and the chemical change of water. So we look at the physical aspect. So this is the physical aspect. Let's just say simple boiling water. What's happening when we're boiling water? Well, what actually happens is when you boil water, you actually just energize the water molecules and you make them want to move away from each other. So when it's a liquid water and you energize them, they vibrate more, they want to expand in different directions away from each other. And essentially, all that's happening in boiling water is you are separating the water molecules away from each other. And that's all that's occurring. On a different note, if we do a process called electrolysis, this is slightly different. We are actually putting in electricity to separate the water molecules into its individual constituents. So we're putting some electricity in to cause the hydrogen molecules and the oxygen molecules to separate from each other and form its own individual gases. How do they do that? Well, we need to go to a concept known as intra and intermolecular bonds. So when we are boiling a chemical, so when we're boiling water, we are only breaking intermolecular bonds. So boiling breaks intermolecular bonds. It's a bond between one molecule to another. So it's a bond between molecules. If you're doing something like electrolysis or electrolysis, you're breaking something a bit smaller, a bit more fundamental. You're breaking the bonds between atoms. Alright, so let's have a look at what's happening when we're boiling water and when we are using electrolysis. Let's look at how boiling water breaks apart the hydrogen bonds, and let's also look at how electrolysis breaks the covalent bonds between the oxygen and the hydrogen atoms. So when we're boiling water, we're actually increasing the distance, the little distances between these intermolecular bonds. When things become hotter, not only do they vibrate more, they also tend to want to move further away from each other. So we want to move away from each other. When they try to move further away from each other, that distance between the molecules is going to increase. And that's essentially what boiling does. It just breaks the distance or increases the distance between individual molecules. So that's what we mean by breaking the intermolecular bonds. When we're completing electrolysis, however, we're actually trying to break the intramolecular bonds between the hydrogen and the oxygen. What the electrolysis does, so electricity uses electrical energy. That electrical energy will kickstart a chemical reaction where the water will decompose the bond between the oxygen and the hydrogen atoms, and they will form the individual hydrogen atoms here and the individual oxygen molecules over here as well. So that's the main difference between the two. The next we have is physical and chemical change with water, what's actually occurring. So let's try and complete some of these questions. So question 1 says, summarize the difference between boiling and electrolysis to highlight the difference between a physical change and a chemical change in electrolysis. Well, we know the main difference lies with where the chemical bonds are broken. So in boiling, it's the intermolecular bonds that we are breaking, meaning that water molecules just separate from each other, but it's still water. In electrolysis, however, we're trying to break the intermolecular bonds. So after this, we're actually creating or producing new substances. If we want to draw diagrams to compare the changes that occur in water molecules in the two process, essentially, if it is boiling, then you are separating the molecules away from each other when you are boiling. If you are using electrolysis, this is slightly different. You are going to break the individual bonds, the individual covalent bonds between the oxygen and the hydrogen. So the electricity comes in here, and breaks it off. And then you get H2 and you get H2O afterwards. Which of these two processes would be easy to reverse? Now, obviously what we do know is if something boils, it goes into the air, precipitates, and then you get rain. Okay, so obviously the process that actually takes less effort to reverse is the boiling. That's a bit easier to reverse. Okay, firstly, it requires less energy to form, so the actual boiling process requires less energy than breaking the individual bonds between atoms. So it's a lot easier to achieve. If we were to look at electrolysis, not only does it require a lot of energy, that's why we use electricity, we also need to do the reverse. So you have to put equals amounts or even more amount of energy to cause that breakage. So the one that actually requires less energy and is easier to reverse is the boiling component here. If we look at this in terms of energy, you only required 44 kilojoules per mole for boiling, and if you compare that to electrolysis, you actually use about 286 kilojoules per mole to separate the individual water molecule, or the hydrogen atom, and the oxygen atom. So in this case, boiling is a lot easier to reverse. Let's look at some practice questions. So the question we have here is, what can we do to write the chemical equations? Okay, so let's look at our question here. The question's asking you to write the balanced chemical equations using the hints that are provided here and the hints provided here. Let's have a look. Okay, so we have barium nitrate reacts with sodium sulfate, and forms a solution of sodium nitrate and a precipitate barium sulfate. So I'll know that barium nitrate is a reactant, sodium sulfate is a reactant, sodium nitrate is a product, barium sulfate is also a product. So if I put these together, barium nitrate, sodium sulfate makes sodium nitrate and barium sulfate. If I want to write a balanced chemical equation, firstly I need to look at all the different constituents. So barium is 2 plus, nitrate is 1 minus, so one would say that it would be Ba bracket NO3 2 plus sodium sulfate. Sodium is plus 1, sulfate is 2 minus, so it would be sodium 2 SO4 becomes sodium nitrate plus 1 minus 1, barium plus 2, sulfate minus 2. So it would be NaONO3 plus BSO4. Okay. If we look at the equation, we can see that nitrate appears twice on the reactant side, and also sodium also appears twice on the reactant side. They only appear once on the product side, so to balance the chemical equation, all I have to do is add 2 here. Also, these are solutions, so AQ, AQ, AQ. Barium sulfate is the solution, or barium sulfate, sorry, is the precipitate. A precipitate is a solid, so there we go. That's the balanced chemical equation there. We go down to 2. We work out that it's aluminium plus hydrochloric acid equals to aluminium chloride and hydrogen gas. Hydrogen gas is H2, it's diatomic. Aluminium by itself is a solid. Hydrochloric acid is aqueous. And then aluminium and chloride. Now chloride is minus 1, aluminium is plus 3. So what we'll have is AlCl3. Okay, so we can see that there are some slight differences. So let's try and balance off the numbers we have here first. So firstly, let's just try and make this a nice even number first. So there's that. We have number 2 there. We have 6 chlorides. And we have 2 aluminium. So I'm going to put a 2 in the aluminium section. Because I have 6 chlorides, I'm going to put 6 here. And then hydrogen on this side, I have 6. This side only have 2. So to make that equal to 6 on both sides, I put a 3. And I will get the following equation. If I want to do a nice fully balanced chemical equation, I need to include the states as well. Aluminium is a solid. Hydrochloric acid is aqueous. Aluminium chloride is also aqueous. And hydrogen is a gas. So there you go. Now let's look at filling out this table. So this table says, what's the difference between a chemical and a physical change? So I did have some answers already pre-recorded, but let's try and fill this out together as well. So new substances, do we form any new substances if it's a physical change? The answer is no. It's just a change in appearance. Do we have a new substance when we have a chemical change? Yes, we do. Particles, what's happening to the particles in a physical change? Nothing, all right? In a physical change, at most, they might be moving closer or further away from each other. So that's just a physical change. What about the chemical change? Well, in a chemical change, the atoms are rearranged. So they're no longer in their original position. They're swapped with another atom. They might have a different kind of bonding, or they might be by themselves. That's what we mean by rearranged. Reversibility, how easy is it to reverse a physical change? Pretty easy. So it's easy to reverse. If it's a chemical change, it would be difficult to reverse. What about the energies involved in a physical change? Small energy involvement. So physical changes can probably happen more naturally, and so it's a very small energy consumption, while as the energy consumed or released in a chemical change is a much larger, so energy change is large. What are some examples of a physical change? Well, we've been talking about this quite a bit, but boiling water. You could even say things like separation of blood. What is a chemical change? Well, we talked about it. We said combustion. We said decomposition. And we also said things like precipitation. So there's that. If you want to have a look at it in a bit more detail, this is the table for you. So pause it here because I'm going to move on. So this question we've already done before, so we're not going to go through it again. However, I just want to thank you all for listening thus far. I'm going to link you back to some previous videos if you want, and also the new video list for Module 3, Inquiry Question 1. Those will be all there. I'll keep recording until then. Thank you for joining, and see you all next time.